So far we have discussed about titanium sapphire laser and how it gets mode locked by itself by something called curved lens mode locking. Now, we are not so lucky in all lasers. Not all lasers would behave like a sapphire laser and get self mode locked, especially when you want to produce picosecond pulses and nanosecond pulses. You have to put in some effort and get the pulses prepared. And one method by which, as we have discussed, you can get short pulses is mode locking. So, there are two ways in which one can achieve mode locking. One is active mode locking, one is passive mode locking. Active mode locking means we put in some device and by applying a voltage or doing something, we try and mode lock the pulses. In passive mode locking, we put in an element to which we do not do anything, but by virtue of some property of this element itself, mode locking takes place. So, in this module, we are going to perform a brief discussion of both these forms of mode locking. So, active mode locking is based on what is called device shears effect, and device shears effect was something that was known decades before the first laser was made. So, you can see this paper 1932 PNAS is where this was published. Now, device shears effect essentially means this: you take a glass of water and put it on a transducer and then apply some sound wave. What you see in the diagram is sound waves have been applied from the top and light goes through in a perpendicular direction. So, what you see in device shears effect is you see something like a diffraction. You do not see one spot going through when the sound wave is applied, rather you see several along the vertical axis in this kind of a setup. Not only that, the beams that are displaced from the mean position above or below are frequency modulated, and the amount by which the frequency is modulated is an integral multiple of omega, where omega is the frequency of angular frequency of the sound wave. So, you can think like this. You see in this diagram, we have alternate layers of light and dark. You have some layers that are white and some are not white. What does this mean? Why have we drawn it like this? No, not constructive interference yet, even before that. All we have done is we have put in some sound wave, right? Now, remember, sound wave is a little different from your electromagnetic wave. What kind of so there are two kinds of waves, right? Transverse wave and longitudinal wave. What kind of wave is sound? It is longitudinal wave, which means it propagates by alternate compression and rarefaction of the medium through which it propagates. So, in this diagram, the dark region stands for an amount of medium which has been compacted, and the light one is where the medium is rarefied. Okay. So, it is very easy to understand in case of a gas, of course, but then this same mechanism happens in liquids and solids, and that is how sound propagates. All right. So, this is essentially depiction of the sound wave that has been applied. Now, see, if you have something like this, a cylinder in which you have alternate regions of high and low density, does it remind you of something that we have discussed earlier, something that you know about? Well, it is like a grating, right? Or you can think it is like a series of slits. Wherever the medium is rarefied, you can think it is a slit, where if it is compacted, you can think that it is a stop. So, what happens when light goes through even two slits? You get diffraction, do not you? And what is the meaning of diffraction? Yeah. So, that is what happens here. So, essentially it is diffraction. Okay. But then, since you are applying sound wave which has a particular frequency, it is not just diffraction, frequency modulation also takes place. Okay. Of course, device shears effect is a lot of mathematics which are not going to go into, that is too much of optics, too much of physics, but we need to know the end result at least. Now, this is actually an undergraduate experiment in physics nowadays. One can buy apparatus like this. So, what you see in the apparatus in the top right panel in this slide, is like an aquarium in which you can fill water. On top of the aquarium you have a transducer, and at 90 degrees laser goes in. In the setup that we have shown here, you can use a red laser or a green laser. And in the bottom panel you can see the spots that you can get if you hold a piece of paper or a photographic film on the other side. And you can see as you change the intensity of the sound, you get more or less number of spots. And what you can perhaps not see here is that the spots are all of different color. Can you see the different color of the spots? You can? I cannot. And I will be surprised if you see. I suspect that white and red is intensity, because see what is the frequency of say red light. Okay, say it in hertz, forget about angular frequency. How much hertz? 10 to the power 4 centimeter inverse, right? Is that right? 10,000, 20,000, 10 to the power 4 centimeter inverse multiplied by speed of light in centimeter, 10 to the power 8 or 10 to the power 10. So, 10 to the power 14. And what is the frequency of sound wave typically? Megahertz, right? So, 10 to the power 14, 10 to the power 6. We are doing 10 to the power 14 plus minus 10 to the power 6. May not be so easy to see. At least I cannot see. You might be able to see, I cannot. But there are instruments that can. Okay. So, this is very roughly what device shears effect is, and this is the beginning of or attempt to do active mode locking. Now, think, why do we see this frequency modulation? Why do we have not only diffraction, but also phase modulation? Because first of all, light is going in from air into whatever that medium is. It can be quartz, it can be a piece of glass, it can be something, some transparent medium. So, that is definitely a denser medium, quartz or glass or water or whatever it is, right. So, what will happen in a denser medium? Frequency will change, is that right? Why will frequency change? Because what is lambda nu? Lambda multiplied by nu, that is equal to what? Actually, it is C by n, is not it? We write C because we always take n to be 1, but it is not the complete statement. C by n, right? So, since n is changing, your frequency and all also have to change, everything changes. So, now suppose I change this n periodically. What am I doing in this transducer? I am applying a sound wave, right? It is not just a block of glass, it is not just a block of quartz, it is a block of glass or quartz in which I am applying a sound wave. Okay. So, as an application of sound wave, your frequency is also going to the refractive index is also going to change periodically, because you are applying a sound wave that is periodic, right. So, that is what leads to phase modulation. The output in time, since we have periodic variation of n1 by applying a frequency, some kind of frequency, the output gets phase modulated. Okay. Now, when you want to do mode locking, you have to work in what is called Raman-Nath regime. Raman is the well known C.V. Raman, Nath was one of his students. Raman-Nath regime means L should be much lesser than capital lambda square divided by 2 pi lambda, where capital lambda is the wavelength of sound, small lambda is the wavelength of light, and L is the thickness of the mode locking medium that you want to use. Now, once again, lot of mathematics we are not going to go into it, right. Whoever is interested, there are a lot of discussions about Raman-Nath regime in say Max Born's optics book, for example. If you are interested, you can read it, but it is a non-trivial exercise if you want to read that book. You need to understand all that math. Okay. So, in Raman-Nath regime, this mode locking phenomenon is observed. Later on, in the next module perhaps, we are going to come across some other regime which is absolutely opposite. Well, L is much larger than capital lambda square by 2 pi small lambda. That is called Bragg regime. And what we will discuss is, in Bragg regime, you do not get this kind of an effect, you get something else. It is close, but not the same. Okay. That is what is used in what is called cavity damping. Right now, we are discussing mode locking, and remember, mode locking can only take place in Raman-Nath regime. Now, what is the only thing that I have control on? I have not only thing perhaps I did not say it correctly. So, I know that when I want to make a mode locker, I have to be in Raman-Nath regime. So, what are the parameters in my control? First of all, capital lambda, wavelength of sound, right. I can use whatever wavelength of sound, it is very easy to produce all wavelengths of sound. Second thing is L. So, by the construction of a mode locker, these things have to be taken into consideration. It is not as if you can take any piece of quartz and apply some frequency, you will get mode locking. It is not the case. Okay. Now, what happens in mode lockers is that you work with not travelling waves, but standing waves. And at this point, let me ask, what is a standing wave? Yes. So, I got this animation. Unfortunately, in the web, the animation is endless. Here it is not. Let us see it with trans. Yeah, see. So, basically, you have this red and blue. Did you see two waves, red and blue, propagating in opposite directions, right? And when they superimpose, they give rise to a standing wave in which the position of the maxima and minima do not change. In fact, the position of the node also does not change. Okay. It just goes up and down, maximum becomes minimum, minimum becomes maximum, node remains the same. I will do it once again, see carefully. So, it is red and blue are travelling waves and the standing wave is in black, right? Yeah, the big wave, blue, cannot be blue. Blue, red, and what is the other color, last color you saw? Green, okay, not black, green. So, look at the green wave, that is a standing wave, see how it changes with time. So, what I have here is that I have a red wave going from one direction to the other, I have an equivalent blue wave travelling in the opposite direction. See what happens to the green one. It is oscillating in such a way that the nodes remain where they are. The maximum displacement, if you do not worry about sign, those positions are also the same. So, this is the kind of wave that you have. Okay. So, this is what you generate, because what you do is you take a quartz crystal or something like that, you have a transducer at one end and polish the other end. So, the sound waves go back and forth and they set up a standing wave, right. Now, the next question to ask is, very often it is easy for us to understand transverse waves, sometimes we get confused when we talk about longitudinal waves. What is a standing longitudinal wave? This is what the situation would be at different times. Let us say this here is your mode locker, you applied sound wave from this direction. So, at first instance, this is the rarefied portion, this is the dense portion, compressed portion, rarefied dense, like that. After some time, it becomes homogeneous. After some other time, what happens is, what was white now becomes black, what was black becomes white. That is the other extreme, where maxima and minima change, maxima and minima interchange, right. Now, tell me, look at this line in time. Suppose a light goes through the middle, then what will the refractive index it experience be as a function of time? To start with, refractive index is high, very high, then it will go down, then it will be very high in the other direction, then it comes to a mean position and then it becomes very high again. So, this is how it will change, right. Of course, refractive index will never become negative, right. It will oscillate between a maximum and a minimum value periodically. And the point to understand here is that the period of oscillation is, it has some relation with period of oscillation with sound wave also. What is the time period associated with a sound wave whose angular frequency is omega? Angular frequency is omega. So, what is the time period? So, from this graph, can you tell me what the relationship is between angular frequency of refractive index and angular frequency of this sound wave, or the time periods, if that helps? Essentially same, right? So, it makes the refractive index change periodically. That is what it does. And this is the experimental setup in an ancient spectrophysics laser. Actually, I have given only this book reference, but this is discussed a little better in E.W. Small's chapter 1, chapter 2 in Topics in Fluorescence Spectroscopy volume 1, right. So, this is an actual diagram of a spectrophysics laser from 3-4 decades ago. The way they did mode locking is that right in front of the high reflector mirror, they put in this prism. Okay. So, this is a prism, light is incident from this direction. The triangular faces of the prism are polished, and on one side you apply a transducer. So, I hope you can see in the diagram that these circles denote these regions of differing refractive index. That is the direction in which the sound wave is applied. Okay. So, what will happen? The omega beam will go in a particular direction. That direction is aligned with the axis of propagation of laser. This omega plus minus n delta go in other directions. So, these directions are not sustained. Propagation in these directions are not sustained in the lasing action. So, you only have omega that can participate in lasing, right. And since the refractive index varies sinusoidally, well, periodically, that is what causes mode locking. Wherever refractive index is the least, that is when light propagates most. And see, intense light is what will propagate with the highest probability, and intense light comes from mode locking. Not only that, the period of oscillation of the refractive index in a mode locker is said to be exactly equal to the period of oscillation of a pulse in the cavity. Okay. So, it acts as a gate, it lets a pulse through, and then when the pulse does a round trip and comes back, there it finds a gate open. Anything that comes in between is not allowed to go through. That is how mode locking is achieved. You cannot use this technique to make femtosecond pulses. Picosecond is where this works most efficiently, right. So, this is active mode locking, and it is achieved by using what are called acoustoptic modulators, AOMs in short, and acoustoptic modulators are used in other applications related to lasers as well. We will come to that. Now, let us talk about passive mode locking. What is the meaning of passive mode locking? In passive mode locking, what you do is you introduce an element in which you do not apply sound, do not apply voltage, do not apply anything. There is some property of the medium by which mode locking is achieved, and the simplest passive mode locking device is a dye cell, very highly concentrated solution of some dye. For the dye has to have some property, we will come to that. This is called the saturable absorber. Can someone tell me what the meaning of saturable absorber is? It has some maximum absorbance. No, see, anything will have a spectrum anyway. Maximum threshold? Actually, that is right. So, that is called nonlinear absorption. That it will absorb the light until, what is the meaning of threshold? Threshold of what?
Means nonlinear response is low intensity light, it will pass through at a high intensity, it will absorb.
Is the other way around. Low intensity light will be blocked, and high intensity light will be allowed to pass through. And we will see very schematically what we mean by that. But before we go there, this would be the typical arrangement of getting mode locking using passive mode locker. So, you keep a solution of dye, and when I say solution of dye, I mean very, very highly concentrated solution of dye. It should be so dark that if you hold it up in front of the light, you should not see any light. That is usually kept right in front of a mirror, and we will see what you can use other than dyes also. But that is not the active medium. Active medium is something else. Okay? So, right now what you see is a schematic, a very general schematic of a laser with a saturable absorber, passive mode locker. And this is a schematic of an actual laser, once again from many years ago. You can see the year of this paper, it was published in 1972, Applied Physics Letters 1972. So, here see carefully what the beam is. It is a dye laser, right, and the dye that is used as an active medium is rhodamine 6G. Where does it absorb, where does it emit? Rhodamine 6G? Yes. So, it absorbs green and it emits in red. Okay. So, this is the cavity. Here you have the high reflector. Well, here you have one of these is the high reflector. Here you have the two concave mirrors, and here this is where the argon ion laser is switched into the cavity by using a prism. And then this here is the cavity. In the other end of the cavity, you have DODCI. DODCI is a cyanine dye. You do not need to know the full name. It is a cyanine dye, and which has rather interesting photophysics, very short lifetime. So, and in fact, lifetime of the saturable absorber is also very important. It should be short if you want a short pulse. So, now what happens is this. You see, this is the emission spectrum, you can say, and emission spectrum of rhodamine and absorption spectrum of dot C. There is a strong overlap. So, dot C would absorb the light that comes out from rhodamine, the emission of rhodamine. Okay. Now, see, let us consider two levels in DODCI, two levels involved in absorption process, and let us say population of the lower one is N1, population of the higher level is N2. So, if you have a small intensity, then what will happen? That will be absorbed, right? When does absorption take place? When does transmission take place? Absorption will take place as long as N1 is less than N2. If you somehow achieve N1 equal to N2, then you get what is called bleaching. Okay. So, if you have a weak beam of light, it will just get absorbed, and then the molecule comes down from its ground state to excited state to ground state, and then it is reset once again. Once again, N1 is very large number, N2 is practically 0. However, what happens when there is a strong beam? If you have a strong beam, then it is possible to almost achieve population inversion, right? Almost, but not quite, almost. And as you know, and as you worked out yourself, pulse light is really very intense. So, let us say we have this laser cavity in which we have CW light propagating and pulse light propagating as well. CW light will be absorbed by the saturable absorber and therefore stopped. So, its propagation will be hindered. Pulse light, because it is intense, will cause bleaching and will get transmitted. Okay. So, this saturable absorber is going to select pulse light over CW light. Okay, so let me show you something. This is the actual data of pulse width. How we measure pulse width, we will come to that sometime later. But this was a pulse width measured in 1972 using this absorber, using this apparatus, using this laser that you see. What is the pulse width written there? Yeah, 2.3 picosecond. So, in this laser you can get almost 2 picosecond was reported in 1972, right. So, here in this setup what is happening is the argon ion acts only as a pump. If there is no saturable absorber, you are going to get a CW operation of the dye laser. Since the saturable absorber has been inserted, that is the only mode locking device there. There itself you can get a pulse width that is as narrow as about 2 picosecond. So, what happens is you can do better than this. You can do better if you have pulsing already and you use the saturable absorber only as a selector, but not as the primary mode locking device. One thing that I want to say before closing this part of the discussion is, and I was actually hoping that you are going to say it, will you agree with me if I say that the pulse gets narrowed as a result of this? See, let us consider that there is a pulse somehow. Mode locking has taken place, that always happens, some amount of mode locking will take place. So, that mode locked pulse is there. Now, if you have a saturable absorber while going through, the leading edge of the pulse is going to be absorbed, is not it? Do you agree? You have a pulse something like this in time, right. Initially at the onset of the pulse intensity is 0, then it goes up gradually, well quickly to a maximum and then it falls again. So, what will happen to the leading edge of the pulse? That will be absorbed and that light will be used to produce, to increase N2 more and more. Then we will reach a time when bleaching will take place and from that instant onward the pulse will go through. Do we agree? So, this induction time for which the population of the excited state is being prepared, that is the time when even the pulse will not be transmitted, it will be absorbed. So, that portion of the pulse is cut off. So, you end up, so let me give you some example. Let us say I have a 20 picosecond pulse, 20 picosecond full width half maximum, and let us say, to keep the discussion simple, it takes 20 picosecond for bleaching to happen. What does that mean? What was full width at half maximum of the pulse now becomes the base of the pulse. So, full width at half maximum perhaps becomes 2 picosecond, 3 picosecond, something like that. Okay. So, it is important to understand that passive mode locking leads to narrowing of pulses as well. Okay. So, we will stop here and we will continue the discussion in the next module.